Analyzing our value stream, we identify several constraints that limit its effective capacity. The most visible constraints are the capacity of the different steps. But there are other, not so obvious constraints, such as the capacity variation of some steps. Process simulation helps us understand the value stream dynamic behavior, how variation affects key process metrics such as WIP, lead time, throughput, cycle time, or on-time delivery. Understanding these dynamic effects will enable us to get to the root cause of problems, implementing definite solutions and not just containing the symptoms. Download this Excel file from OneDrive onto your PC and enable macros to run this value stream simulator. In sheet capacity, we see an ideal 3-step value stream. Each step has a process capacity of 100 units and our commitment to the customer is 100 units on every period. Press the Start button to run the simulation and we can see the periods advancing, but otherwise nothing else seems to move. On-time delivery is 100%. This is an ideal process. WIP is 100 and lead time 1 in every step. Press Halt to stop simulation. Change Step 2 capacity to 90, press Enter. Press the Start button. Now answer these questions. What happened to percent on time? Where is the queue building up? How is lead time affected? Why? First priority, customer satisfaction. How can we improve delivery performance if the bottleneck cannot be improved? How about renegotiating the delivery commitment with the customer? In a normal situation, it is possible to compensate for a lower capacity in one department by working a bit faster to catch up with the work or by working overtime, etc. There are, on the other hand, some cases where there is a physical limitation which cannot be compensated by overtime, or there are legal constraints, etc., which prevent it. In a case like this, where there is no possibility to open up the bottleneck, all that is left to do is tell the customer and renegotiate with him volumes which are in line with the bottleneck capacity. Setup, continue from previous exercise. Press the Halt button. Change commit to 90, press Enter. Press the Start button. How is percent on time now? Is the line, queue, still growing? What is happening to lead time? Why? How can you stop the line from growing further? How about limiting the line starts to the bottleneck capacity? The bottleneck is therefore dictating how much you can commit to your customer, but it also dictates how many items you should start at the beginning of the line. Starting more than the bottleneck can handle is a waste. The number of units coming out of the line, throughput, will be equal to the bottleneck capacity, and therefore all the units started above that capacity will simply pile up in front of the bottleneck, increasing not only the inventory but also the lead time. Setup, continue from previous exercise. Change Step 1 capacity to 90. Questions. Is the queue still growing? What about lead time? Why? Why do we still have a queue if the problem has been solved? How can you reduce the queue? How about limiting starts below delivery level for some time? By controlling both the output and input to the line based on the bottleneck capacity, we can now say that the problem is solved. But is it really? We see that the lead time is still too large, and this is due to the excess inventory which has accumulated in front of the bottleneck. Something similar happens when we have been overeating during holidays. Going back to normal eating habits is just not enough if we want to get rid of the extra kilos. In this case, therefore, you must flush away the excess inventory, and one way can be to limit starts below the throughput level until the excess is depleted. Setup, continue from previous exercise. Change Step 1 capacity to 80. Run, press Start, until the excess inventory is depleted, press Stop. Change back Step 1 capacity to 90, press Start. Observations. What happened to AV WIP when you limited starts below delivery? Why? What happened to AV lead time? Why? Did you miss any deliveries during this operation? How can you reduce excess WIP otherwise? How about applying just in time? Now we can confirm we have solved the problem. We are committing our deliveries to the customer in line with our actual capacity, as dictated by the bottleneck. We are systematically meeting our commitments. We are keeping an inventory level in line with this, and our lead time per step is 1. Another way to eliminate the excess inventory in the line is to apply just-in-time. This consists basically in banning the accumulation of inventory by decree. The way to do that is to work in pull mode. You only produce if there is empty place to put your output. That empty place will only be created the moment the next step in the line removes an item from your output buffer. With this logistics, nobody processes more items than the ones going to the customer, and in case of excess inventory, the corresponding steps stop processing until the excess is depleted. To simulate this method, we have filled the line with inventory by having capacities well above commit and running for a while. Then we press reset to put capacities back to 100. Now we have a balanced line, but due to past problems there is an excess of WIP which causes a large lead time. We will now apply just-in-time to remove this excess WIP. Apply JIT, set all max queues to 200. Start the simulator and watch the effect. Questions. What happened to the WIP? Did you miss any deliveries? Is this method of reducing excess WIP safer than the previous one? Apart from the capacity bottleneck experienced before, there is another type of bottleneck which is generated by the fact that a department has high variability in its performance. Although very often both types of bottlenecks will be combined in the same department or process step, we will isolate the pure variability bottleneck, same average capacity as the rest, in order to see its effect on the total process. Typical variability bottlenecks are checking or approval steps, where some items take very short, but some others may take much longer. Public services, or services which are outside our control, may typically show also high variability. Poor quality also generates variation because you must repeat some operations on some of the items. Equipment failure or low performance can also cause variation. When several concurrent inputs are required for a certain process step, it will happen that they will not arrive at the same time, therefore one may have to wait until the last one arrives. This is therefore another source in performance variation. Setup. Halt simulation. Reset. WIP clean. Set step 2 variation to 20, capacity varies at random between 80 and 120. Start simulation. Questions. What happened initially to percent on time? What is the average production of step 2? Who is causing the problem in the line? Is he likely to admit it? Why? Where is the WIP building up? Is percent on time improving as WIP builds up? Why? What happened to AV lead time? What can we do to reduce lead time? How about applying just-in-time? The purpose of JIT is to reduce excess inventory, leaving the absolute minimum required to operate. By doing this, waiting time will be reduced and therefore the total lead time will also be reduced. But does it have any side effects? Setup, continue from previous exercise. Set max queue to 200 in all steps. Questions. Percent on time? What is the average throughput of all steps? Which step is causing the problem to the whole line? Is it obvious if we just look at the average throughput line? Has lead time improved by applying JIT? Can lead time decrease and on-time delivery get worse? Would you recommend this solution? Why? What happens if you have high variability and apply JIT? In a case of high variability, how can you reduce lead time and still meet your commitments? How about reducing capacity utilization? Assuming we are not able to eliminate the root cause of the problem, variability in step 2, How can we meet our customer commitments, and at the same time reduce lead time? We will try reducing capacity utilization, which means that we will not commit to our customers 100% of our process capacity but only 95%, leaving the 5% balance to compensate for the variability of step 2. Set up. Halt simulation. Reset. Clear whip. Set step 1 capacity to 95. Set step 2 variation to 20. Set commit to 95. Start simulation. Questions. Percent on time? What are the following values after stability? Average whip? Average lead time? What are the negative effects in this case? What is the throughput in the line? Would you recommend this solution? Yield loss or items lost during the process. This loss may be due to defects that force us to scrap an item, or it may be due to the item being rejected in one of the control/approval steps. Set up. Halt simulation. Reset. Clear whip. Set step 2 yield to 90. Start simulation. Questions. What is the total throughput in the line? Is lead time affected in this case? How many units do you start in the line on each period and how many do you finish? Processed in step 1? Throughput? What happened to the difference between started and finished units in the case of a capacity bottleneck? And in this case of a yield bottleneck? In a process where items are lost or rejected in several steps, we want to know what the total process yield will be as a function of the step yields. This is what we call compound yield. Set up. Set all step yields to 90. Questions. What is the total line throughput? Is this what you would expect? So the total yield is the product of the step yields. 0.9 times 0.9 times 0.9 is equal to 0.73. Is 90% step yield acceptable? What would happen with a larger number of steps? What happens to the difference between the units started and those delivered? How can we estimate the capacity requirements for each process step in case of yield loss? What we want to achieve is deliver the customer requirements with the minimum capacities possible. Assumption. Yield equals 90 in all steps. Objectives. Commit equals 100. Percent on time equals 100. Estimate the minimum capacities required to achieve this. Solution. Capacity, step 3, equals 100 divided by 0.9 is equal to 111. Capacity, step 2, equals 111 divided by 0.9 is equal to 123. Capacity, step 1, equals 123 divided by 0.9 is equal to 137. Set up. Halt simulation. Reset. Clear whip. Set step 2 batch to 5. Start simulation. Questions. Is the batching of step 2 affecting the throughput of the total process? Is it affecting on-time delivery? What is the effect in whip? AV whip? How is lead time affected? AV lead time? Why? In real life we will not find single effects as seen so far, but rather a combination of the different effects. When several effects coexist, we will not find a single optimal solution. Depending on the relative cost of capacity versus inventory or lead time, the optimal solution will vary. Typically, increasing capacity drastically will solve the problem, but it will be an expensive solution. Set up. Select Simulator tab. Halt simulation. Reset. Clear whip. Yield equals 99 in all steps except number 1. Variation equals 10 in all steps except number 1. Objectives. Percent on time equals 100. Minimum average capacity, AV cap. Minimum lead time, AV lead time. Proposed solution. Enter capacities and maximum Q for each step. Let us now recap the effects of the different types of bottlenecks seen so far. The capacity bottleneck causes a drop in throughput and an accumulation of WIP which increases lead time. The variability bottleneck causes an initial throughput drop when the line is empty, but it recovers when WIP accumulates, causing as a result an increase of lead time. When we have high variability, and we apply JIT, there is a significant drop in throughput but WIP and lead time are kept low. A yield bottleneck causes a drop in throughput like in the case of capacity, but in this case, there is no accumulation of WIP and, therefore, lead time is not affected. The case of batching is like a variability bottleneck, but in this case this variability is repetitive and predictable. Therefore, the initial increase of WIP and lead time remains constant. These are some conclusions. An instant picture of your value stream may not be enough to understand what is going on. Variation is like a virus which passes undetected unless you are aware and measure it. Waiting times may be caused by variation, in which case you will not be able to reduce them unless you attack the root cause of variation. Different types of constraints cause different effects which need to be understood in order to improve them. Pushing product through the value stream above the bottleneck capacity will only increase WIP and lead time but not throughput. Applying just-in-time to a high variability process is a formula for disaster. See the article in Polyhedrica blogspot.